Hello friends, in this video I am going to teach you about logic gates. It is the one of the important thing in digital electronics and logic design. First let's see the outcomes of this video. The first outcome is definition of logic gates. In this I will teach you what is the exact definition of logic gates and what are the different types of logic gates. And next let's see the different types of logic gates. Those are AND gate, OR gate, NOT gate, XOR gate, XNOR gate, NAND gate and XNOR gate. Okay, first let's see what is the logic gates. Okay, logic gates. Here logic gates are very useful in order to design the digital system because it is used to perform the logical operations. Let's see what is the definition for logic gates. Logic gates are the building blocks of any digital system. Okay, in order to make any digital system, these are the basic building blocks. Okay, it is an electronic circuit having one or more than one input and only one output, which means every logic gates having one or more inputs but only one output. According to the logic, it will generate only one output, not input. The relationship between the input and output is based on the certain logic, which means based on the logic of that particular gate, it will produce the outputs, and the input and output relations are also obtained based on the particular logic. Here, based on these logic gates are named as AND gate, OR gate, NOT gate, etc. Here are the some of the logic gates. Instead of this, we have also NAND gate, NOR gate, XNOR gate, XOR gate, like that. First, let's see what is AND gate. Okay, it's a basic thing. AND gate. Here, let's see the definition for AND gate. The output of logic gate is 1 when the both inputs are ones. If any one of the input is 0, then the output will be 0. It is the input output relationship for the AND gate. Here, this is the symbolic representation of the AND gate, and AND gate having always two inputs. Let's see one input is A and another input is B. It performs the AND operation. Let's see logical AND operation. AND operation is nothing but simply a multiplication operation. If these two inputs are 1 and 1, we know 1 into 1 is 1, that is output equal to 1. If any one of the input is 0, that means 0 into other term is always 0, that's why we get the output as 0, which means AND gate is a logic gate which is used to produce the output, and that output is 1 only when both the inputs are ones and the output is 0 whenever at least one of the input also 0. Okay, and it is the truth table for AND gate. Here see, it is the inputs A and B and Y is the output. We know it is perform the multiplication operation, that is input is A and B is also input. Multiplication of both A and B is our output. Let's see the combinations for A and B, that is 0 0, 0 1, 1 0, 1 1. Here 0 into 0, we know 0 into 0 is 0. Next one is 0 into 1, we know 0 into anything is 0. And the next 1 into 0 also 0, and here 1 into 1 is 1. This is about AND gate and its truth table. Next, let's see what is OR gate. Here, OR gate. AND gate performs the multiplication operation on the inputs. Here, OR gate is used to perform the addition operation on input. Okay. Let's see here what is OR gate. If any one of the input is 1, then the output of the OR gate is 1. If two inputs are zeros, then the output of the OR gate is 0, which means it performs the OR operation. Here also we have two inputs. Let's see, it is the symbolic representation for OR gate. Here we have two inputs, one is A and another one is B. If both inputs are zeros, 0 0, we know it performs the OR gate performs the addition operation, that is 0 plus 0 is equal to 0, that is output is 0. If the input is 1 0, that means 1 plus 0 is equal to 1, then output will become 1, which means if any one of the input is 1, then the output is 1. If two inputs are zeros, then only the output will become 0 in OR gate. Let's see the truth table for OR gate. Here A and B are inputs and C is the output. If inputs are 0 0, then 0 plus 0 equal to 0, then output also 0. If inputs are 0 1, 0 1 means sum is 0. Next 1 0, 1 0 means also sum is 1. Next coming to 1 plus 1. In 1 plus 1 also we have sum is 1. Okay. This is about the OR logic gate. Now coming to the NOT logic gate. It is NOT gate. Here NOT gate is nothing but it is used for complementing an input term. It performs the complement operation. If we give the input as 1, then it produces the output as 0. If we give the input as 0, then it gives the output as 1. That means it performs the complement, one's complement on the input data. This is also known as complement gate. Here NOT gate performs the output of the NOT gate is 1 when input is 0 and output is 0 when input is 1. That means it performs the complement operation. Here let us see, it is the symbolic representation of NOT gate. Here let us see, if we give the input as A, then we get the output as A bar. That means if you give the input as 0, then the output is 1. If you give the input as 1, then the output will become 0. This is about NOT gate. Let us see the truth table for NOT gate. Here NOT gate is always having only one input. Okay, remember that. And here NOT gate having two inputs. NOT gate is having only one input, but we have to cover two combinations, that is one is 0 and second one is 1. Okay. If we give the input as 0, then the output will become 1. If we give the input as 1, then the output will become 0. It is about NOT gate. Now coming to the next gate, that is XOR gate. It is very important gate. In most of the digital systems we are using XOR gate operation. Okay, let's see what is XOR gate. XOR gate is a digital logic gate that gives a true output. True output is nothing but 1. True means 1 and false means 0 when the number of true inputs is odd. Okay, I hope you understood. If we have so many inputs for XOR gate, if the number of inputs of the XOR gates are 1, that is odd ones, then we can get the output as 1. Okay, number of true inputs are odd, then the output also true. If number of true inputs are even, then the output will become 0. That is about XOR gate. Let us see, this is the symbolic representation of the XOR gate. Here the inputs are A and B, and this is the output of the XOR gate, that is C is equal to A XOR B. This is the symbol for XOR operation. Okay. Let us see here the truth table. Here A, B are the inputs and output is A XOR B. If we give the two inputs as zeros, 0 0 means here we have even number of ones. There is no one means even number of ones we have. Then the output will become 0. Here observe 0 1. Then we have only 1 1. 1 1 means odd number of 1 is there. Whenever we have odd number of 1 inputs, then the output will become 1. And here also 1 0. 1 0 is nothing but here also we have odd number of ones. Only 1 1 is there. That's why the output also 1. Here let's see 1 1. Here 1 1. There are two 1 1s. 2 means what it means? It is the even number of ones. Whenever we have even number of ones, then the output will become 0. Here it is the Boolean expression for XOR gate. Okay, A B bar plus B A bar is the Boolean expression for XOR gate. If we substitute A and B values in this expression, then we can get the outputs instead of remember this truth table. Okay. Now coming to the XNOR gate. XNOR gate is the exactly opposite to the XOR gate. Okay. Here let us see the definition of XOR gate. The XOR gate is a digital logic gate whose function is the logic complement of exclusive OR gate, which means we know the output of the XOR gate. The output of the XOR gate is 1 whenever there are odd number of input ones are present. If even number of input ones are present, then the output will become 0. It is exactly opposite to the XOR gate. That's why if we simply complement the XOR gate output, then we can get the XNOR gate. Okay, here it is the symbolic representation of the XNOR gate, and here output will become C is equal to A XNOR B, and this is the symbol for XNOR gate, one circle, and in between the circle we have one dot, that is the XNOR gate. Now let's see the truth table for XNOR gate. Whenever we have even number of ones, then only the output will become 1. Whenever we have odd number of ones, then the output will become 0. It is opposite to the XOR gate. Here let's see 0 0. Here we have even number of ones, that's why the output will become 1. Let's see here, next input is 0 1. Here we have only 1 1, that means it is having, here we having only odd number of ones, that's why the output will become 0. Here also 1 0, odd number of 1 is there, that's why here we have the output is 0, and the next one is 1 1. Here also we have even number of ones, that's why the output will become 1. Now coming to the next logic gate, that is NAND gate. It is the one of the important logic gate in whole logic gate family. Okay, we already discussed about AND gate. It performs the multiplication operation on both the inputs. And NAND gate is nothing but the complement of AND gate result will give the NAND gate. If we complement the AND gate result, then we can get the NAND gate outputs. Okay, now let's see first what is AND gate. AND gate is already told you, whenever we have both inputs are ones, then only the output will become 1. If any one of the input is 0, then the output will become 0. That is the AND gate. Now let's see what is NAND gate. The output of NAND gate is the complement of output of AND gate. I already told you it is the complement of AND gate output, then we can get the NAND gate. It is the symbolic representation of the NAND gate. I already told you, whereas in the case of AND gate, the output is the A into B, that is A dot B. Here NAND is the complement of AND, that's why I write here bar, A dot B bar, that means complement of the multiplication. Here let's see the truth table of the NAND gate. If we give the inputs 0 0 for NAND gate, whereas in the case of AND gate we get the 0 as the output, but it is the complement for that one, so I write here the output as 1. If we write the 0 1, here the output is 1, 1 0 also output is 1, for 1 1 only the output is 0, whereas in the case of AND gate for 1 1 only the output will become 1, in all other cases the output will become 0. Here exactly opposite for the than the AND gate. Now coming to NOR gate, it is the last classification of logic gates. Here it is the exactly opposite to the OR gate. NAND gate is opposite to the AND gate, NOR gate is opposite for the OR gate, and NOR gate outputs can be generated by complementing the output of the OR gate. We simply generate the NAND gate outputs by complementing the outputs of the OR gate. Let's see here, the output of NOR gate is complement of OR gate. Okay, let's see, this is the symbolic representation of NOR gate. Already told you, whereas in the case of OR gate, the output will become as the addition of two inputs. Here also the addition of two inputs is the output, but with complement. With complement, the addition of two numbers or two inputs is known as NOR gate. Now let's see the truth table for the NOR gate. If we have inputs as 0 0, then the output will become 1. If we have inputs as 0 1, the output will become 0, and 1 0 means 0, 1 1 means 0. It is the truth table also exactly opposite to the OR gate. That means finally I conclude that if we know or if we strong in AND gate, OR gate and NOT gate, and remaining all other gates are very easy. We can generate by using that gate only. Okay. I hope you understood this topic. Thank you for watching this video.